So Numpy is trying to be smart about the ordering. So if you have two arrays and one array is ordered with this C ordering and the other one is ordered with the F ordering, and you try to add these two arrays, right? Then you have to be really careful that they're basically not compatible, and you do have to do some data reshuffling before you can add them. But Python is smart enough about this, and you get the expected result out. So 1 plus 1 is 2, 2 plus 2 is 4, and so on. So you don't get messed up just because you have matrices with different orders. And so the reason why it's useful is because it can, if you want to transpose the matrix, so transpose means just basically flipping. So rows become columns and columns become rows. The way you can do that now is really, really cheap in Numpy, because all you need to do is you need to change that the C in the Fortran ordering. So when you call a.transpose, so that's this flipping process, then so originally A was in C contiguous mode, but after we've transposed it, then it becomes a Fortran contiguous mode. And so that's how transpose is implemented. Okay, so the next part I want to talk about is array indexing. So first, the basic indexing that we know already from lists work just as well also in Numpy arrays, which means that, in particular, it means that we can do things like slicing. So if you have a one-dimensional array and we want to get the second to the fourth element, then we can write A1:4. So that gives us everything from index 1 to index, between index 1 and index 3, which is the second to the fourth element. There's also something called fancy indexing. So this means that you can, let's say you want to get the entries 0, 2, and 3. The way you can do that is you just pass in a list of indices that you want. And so, sorry, this are the entries 0, 3, and 4 here, because indexing always starts at. So it's the first index. Oh, sorry, that was correct. So it's get entries 0, 2, and 3. Yeah. So the important part here is that when you do the slicing, you actually get a view on the underlying data. So there's no copying going on. Instead, you kind of get just a new Numpy array that points to kind of a subset of the original raw data. That makes the slicing extremely cheap because no copying is going on. On the other hand, if you do the fancy indexing, so there you do get a copy of the underlying Numpy array. So that's the difference. So then we can also do, we can use the same indexing to set values. So let's say you have the vector and you want to set the second and the third element to -1. Then you can just use the notation like here. The same thing if you want to set the last element equal to be the first one. You can use the negative indexing. And if you want to set all elements equal to 0, you just use a colon. That basically means starting from the first element all the way to the last element. So you kind of slice out everything, and then you set all elements equal to 0. The same thing works for multidimensional indexing. So now if we have, we create a matrix with 2 rows and 3 columns. And then what we can do is we can set, so now when we do indexing, we need to provide the indexes of both dimensions, right? So if I want to have the second row and the third column, I set equal to 10 here. You can do the same thing by doing first extracting the first row, and then you get a vector out, and then you get the third element of that vector and set it to 10, right? So that's these two are actually equivalent. The second one is slightly slower because you first have to extract the vector, and then you do another query on that vector. While on the first solution here, you get immediately the element that you're looking for. So if you want to get an entire column, you just use the colon syntax. So here you just specify I want all elements, and then you specify the column that you're interested in. So here, these are all the row elements for a fixed column, the third column, right? And that means you get the third column. The same thing works here. So here you specify, okay, I'm interested in the second row, and I'm interested in all column elements, which means you get a vector with the second row. And then if you want to set all elements to 0, you can just do a colon, comma, colon equals 0. So let's look at an example. Let's say you have a matrix. This is a fancy way of creating a matrix. So I just say NP lin space. So I create a linearly distributed points, in total 30. And then I reshape it to a 5 times 6 matrix. So then I get a matrix like this. And so now, let's say I want to extract a submatrix. I'm only interested in part of that. So we can use our slicing. You can use our slicing syntax. And you will now see how powerful this is. So let's say we want to get the submatrix consisting of row 2 and 3, but we're only interested in every second column. So the way we do that is, okay, I'm interested in row 2 to 3, so I use the normal slicing notation here, 1 colon 3, right? And then, remember also in slicing, when we have a second column, we can specify a gap between the elements that we want. So here I'm saying I want to have all the columns starting from the first column, ending at the second column, but only every second one. So this is the result that you get. This is now the second and the third row, but only every second column starting from the first column. And so there's no copying going on. We're still working with the raw data, and we can now operate this, right? So I could, for example, I could just set this to 0 now. And so now if I printed A, you'd see that I have zeroed out exactly these elements in my submatrix. Okay? So the same thing works. Let's say we want to have the submatrix consisting of every third row and every second column starting from the third row. It's essentially exactly the same idea, right? So I use kind of these 2 colons to specify that, and then you get that submatrix. Oops. Yeah, and as I mentioned, so when you do assignments on the sliced array, you will actually change the original array as well. And that's because you just have a view on it. You don't have, you're operating on the same raw data. So it's exactly the same example that I had before. So I have a matrix A that just consists of ones. Then I extract the submatrix. Then I set the first component of that submatrix and print it. And then you'll see that also I print the original matrix back, and you'll see that the original matrix has changed as well. If you want to avoid that, so if you want to make a slice, but you really want to have it as a copy, so that you can change that submatrix without changing the original one, you need to use the copy function, right? So the copy function just takes the array and creates a copy of it, of the underlying data, and then returns you that copy of that array. So that way you get its own raw data, and then you can operate on the 2 Numpy arrays separately. Yeah, so there's a difference here between the Python lists. So when you in Python, if you do a colon, then you always get a copy back. While in Numpy tries to do as little copying as possible, and only if you do it explicitly, it creates a copy. So then we have loops. Let's say quite often you might want to loop over all the elements in an array and perform operations on it. So if you know the dimension of the array, then you can do a nested loop over each individual dimension, and just loop over the length of elements in each dimension. So for example, if I have a matrix, I could write for I in range A shape 0. Right? So A shape 0 gives me the number of elements in the first dimension. And then with range, I just loop over all the indices in that. And then I do the same thing for the second dimension. So I now use A shaped 1 to get the length of the second dimension. And then I can do standard indexing here to update the element in the matrix. So that works perfectly fine, but it's not very elegant. So we could ask, is there maybe more Pythonic? Maybe this is something you would do in C. Is there a more Pythonic way of doing it? The other problem is, what if we don't know what the dimension of the array is? So a better, more Pythonic way of doing that would be to use standard Python loops. So the way you would do that is you write for row in A. So in that part, you would now you would loop over all the rows in that array. And then for the second part, for the second dimension, you write for element in row. And then you get each element out. And then you can call that function. But that still doesn't, so here you still need to know which dimension you have, right? Because you need to nest, you need to have as many for loops as you have dimensions in your array. So what, so here the difference is we had to explicitly get the indexing. And so I've converted that now into standard Python loops. So if you have an array with unknown dimensions, the trick is to convert that array into one-dimensional array and then loop over all the one-dimensional array. And so essentially, and so it's the a.revel function that allows you to do that, right? So if you have a arbitrary dimensional array in Numpy, we could change its shape to be one-dimensional and then just have loop over that one dimension. But there's a shortcut. You can just write a.revel, and that basically gives you a view on that matrix or whatever it is as a one-dimensional array. And then your loop becomes just for element in a.revel, where a.revel is now a flattened view on that array. So a.revel tries to avoid copying, but in some cases it might actually need to copy. But you can, it always ensures that you can loop over all the elements in that array. So just an advice, so a.revel is most useful when you want to read over all the elements in the array. And so the reason is because it might return a copy. So if you're trying to assign to an array, then it's better to use shape or reshape to make sure that you're not accidentally assigning values to a copy instead of the original array. And then finally, if you want to loop over an array with, and you also need is indices, right? So up here we only had access to the element, but maybe you only also want to know on which index is that element, in which row, in which column am I working on. So if you want to do that, then you can use np.nd enumerate. So np.nd enumerate gives you allows you to iterate over all the elements in an array, and you get the index and its value. And so if you do that for a simple case and you print the index and the value, then you'll see for a two-dimensional array, the index always consists of two numbers, namely the index of the first and the second coordinates, and then the value of that item. Does it make sense? Maybe? Yeah. Okay, array computations. So one thing that is really quite different to a Numpy array is if you do arithmetic operations, they're considered element-wise. So when you write b equals 3 times a minus 1, and a is an array, then b becomes an array, and it's the element-wise computation. So implicitly what's going on in this line is you're taking each element of a, multiplied by 3, and then subtract 1. So this behavior is different to lists, but it's more useful when you do scientific computing, right? Because that's often what you want to do. You have an array, and you just want to multiply all the elements in that array by a number, or you want to subtract a number from that array. So essentially what's going on here is, well, you compute each element multiply each element by 3, and then you subtract 1 by it, and then you get the result out. So the reason why this is so important is because these array operations are much, much faster than element-wise operations. And I just want to show that to you. So let's try this now in an experiment where we have a 10 million large array with 10 million elements, and we're trying to do an element-wise operation compared to these vectorized operations. So here's the element-wise implementation. So I have an array here, A equals lin space, so linearly spaced elements with 10 million elements. And the idea is that I want to multiply each element by 3 and subtract 1 from it. So the way I do it, okay, I start a clock here so that I can time it, and I end the clock here to stop the timing. So this just allows me to evaluate how long this piece of code takes. So what I do is first I create a new matrix of the same size as A. Then I loop over each element in A and set the associated B value to be 3 times A, the element A minus 1. Okay? So this would kind of be our standard implementation. So now I'm running it. So let's see how long this takes on 10 million elements. There we go. Okay, so this took 12 seconds. So let's now try the same thing, but with our vectorized version. So again, A is, maybe I should, so A is still our NP lin space, so nothing has changed. And now I just write B equals 3 times A minus 1. And by doing that, I'm now making use of the Numpy vectorization. And if I run this, okay, so that took 0.12 seconds. And so in other words, if we now compute the speed up, right, so that we just saved 103, our vectorized version was 103 times faster. Right? So that's something you keep in mind. So if you have, that's how you really get the speed up, right? So Python loops in generally are slow. So if your code is slow and you have identified where it's slow, then the first thing you should ask yourself is, am I operating on Numpy arrays, and have I implemented Python loops? And if you have done so, then it's time to use a vectorized version of that loop instead. So, so the most common thing work immediately vectorized, like the multiplication or subtraction. If you want to have maths functions like sinus or cosinus and so on, then you can use, so Numpy has all these or many functions implemented. And so you just call them with np.sin or np.arcsine and np.sinh, for example. And so you just need to make sure that you call the Numpy version of these mathematical functions. And so all these exist for log, exp, square root, and so on. So you can also use the maths functions from the math module. So normally when we do maths in Python, right, we write from math import sine. This will also work on Numpy arrays, but it will be slower. So if you want to have best performance, then use the Numpy implementation and not the math implementation. So then one thing that is quite useful is, so sometimes you want to, maybe your function that you want to apply on an array is not implemented. It's not implemented in Numpy. But you would still want to benefit from the vectorization. So here's an example. Let's say you have your own function implemented, and you want to apply it to all elements in that array. So here's my func. I just say if x is larger than 0, then return 0, and otherwise return x squared. Okay? So there's no, we can't really represent that in standard, as one standard Numpy function, so that's why I wrote my own one. But now the problem is if I call my func a, okay, so then I'm passing in a vector a into that function, right, and an array into that function, and then Python will do things like array larger than 0, right? And this doesn't make sense. I mean, what I want to say is that I want to apply that for each element instead of the entire array. So in fact, if I execute this, it just throws an error, and it crashes on this line where I'm comparing now an array with 0. That just doesn't make sense. So what I need to do is so the problem is that my func operates on the entire array instead of each element. So our potential solution would obviously to loop over each array element and call my function, but that's really slow, as we learned, so we need to find something better. And so that something better is to vectorize that function. And so Numpy provides a functionality to do that. So when you call numpy.vectorize, you can pass in a user-defined function, and it will return a vectorized version of that function. And so now, after I've done that, I can call my vectorized function on the Numpy array, and then it will do exactly what I wanted to do. Does that make sense? Yeah, so this is just a list of other, of more array operations that might be useful at some point. So yeah, I won't go through them, but just for completeness if you're interested. Last part for today is plotting. So we talked a lot about creating arrays, doing maths on arrays and so on, but really at some point it's also nice to plot the data so that we can see what we're actually working with. And so the most common package that we have in Python is called matplotlib, and it's also part of your standard installation. And so in particular, the module pyplot is the one that is often used. And if you're already used to MATLAB, you'll see that actually the user interface is almost the same. So matplotlib can be sometimes a bit overwhelming in terms of its functionality. And so in particular, if you want to do more complex plots, there's a bunch of resources that you can use. And so in particular, what I often do, if I want to create a more complex plot, I go to this matplot gallery. So there's a link, you can just go there. And it basically shows you, I think there's probably 100 different plots. And then you can just search the one, you can just find one that is appealing to you, and just click on it, and then you get the source code for that plot, and then I'd normally start adapting that. So that's a really good way, or easy way to get started for more complex plots. But let's start with the simple plot first. So what you need to do for a simple plot is you import the matplotlib or the pyplot module of matplotlib. Then you need to create some data. Let's say you have some x coordinates, and then you create some y coordinates. You evaluate a cos function and an exponential function on these coordinates. And then it's fairly straightforward. You just type in plt.plot xy to plot the x and y points. And then the same thing for x and z. And then plt.show will show you that plot. So here, keep in mind that I'm just plotting a bunch of points, but Matplotlib actually interpolates these points and shows me them as a line. So they're kind of piecewise constant, but we don't see it because there's so many. But it becomes maybe more apparent. I think actually, if I just have 5 points here, yeah, so yeah, now you see what's actually going on, right? So it's interpolating between. So then it's quite common that you want to adjust your plot. So for example, you want to change the line colors, the thickness, and so on. Maybe you want to add an x-axis on it and add a legend. And all this is fairly straightforward. So when you call the plot function, you can provide a label. So this label is showing up in the legend. You can specify the color of the line. You can specify the line width and the line style. So a single minus just means a solid line, and a double minus means a dashed line. And then there are various other options that you have. You can use the X label and the Y label functions to add labels to that plot. And you can use the legend function to show the legend. So I'm not actually sure if I show this, but there's also a save fig function, and that saves that plot to file. So that's often quite useful. So you can say save fig.file.pdf, and now after that you actually have the PDF file, and you can include it into your thesis or whatever. So, yeah.
Are we going to have to make some small animations or something? Because I know you can always also use plotting for making a small animation of moving maybe away from something over.
So if you want to do animations, so that's.
I was just wondering if it's something we're going to do.
No. It is possible in Matplotlib, but so Matplotlib is, at least I use it mostly to create plots for publications, right? So if you in a reproducible way. So. Yeah, but I know there's some functionality for animations as well, but I've never really used it much. Maybe Min will show you that in 2 weeks, how to do animations in iPad Notebook. Okay, so there's a bunch of other plot types that you can choose from. So you have scatter plots, bar plots, contour plots. You can show images, pie charts, and 3D charts. Yeah, and so they're all the associated function names. So here's an example of a scatter plot. It works exactly the same way. We just use pld.scatter with the x and y points, and then specify some coloring. Sometimes it's useful to plot a function, f. So the way, let's say you want to plot f of x equals x minus 3, x minus 5, x minus 7 plus 85. So what you do is you first implement that function. Then you need to decide on which, you need to decide a bunch of coordinates where you want to evaluate that function. So use linspace for that to get kind of equally spaced evaluation points. Then use Numpy's vectorized. Make sure that all these operations here are already vectorized, or if not, then you need to vectorize that function. But either way, so call your function on this array, and then you get a new array out with all the function values, and then you can just call pld.plot. So that's a very common way of doing that. But keep in mind that when you use func and you use some non-vectorizable things like if statements, then you need to vectorize that function first. Yeah, and then obviously we can change the colors and so on. Yeah, combining two plots just means calling plot twice. There's nothing magic here. The final thing that I want to mention is that at least I think the normal plots look really ugly in Matplotlib. So there's a trick. There's just a one-liner that allows you to make the standard plots much, much prettier, and that one-liner is import Seaborn. So Seaborn is a package for statistical data visualization, and it also overloads the standard Matplotlib style. And so, yeah, so I just think this looks a lot prettier than the standard matplotlib packages. So just write import cbon at the beginning, and then automatically all your plots will look, in my opinion, prettier. Yeah.
Here, if you ran the code like the normal version with import matplotlib as PLT and stuff like that, is that for for the cbon?
Right. Yeah, that's a good. Yeah. So here I definitely you need from matplotlib dot pyplot import import. No, so 1 second. From import SPLT. And you also need Numpy, yeah, to have it. Okay, so now you have a complete example. It's just that so in IPython I keep executing the code from previously, so that's why it was already imported.
I actually have 2 questions.
Mm-hmm.
When you call the lens space function without specifying the end, what's the default value of n?
Okay, where did I do that?
I think it was the last slide. Where you put a function into the plot.
All right.
So you see x does not have you haven't chosen how many points you
Right.
want.
Right, that's a very good point. I think, so let's try it out. I think what's going on is that it just uses 1 as a default. No. Okay, so I don't know. Let's check.
I think it's 50 by default.
Yeah, okay. Yeah, you're right. Okay, so the default is 50.
All right. And then the second question I have is, what does it mean if a function is vectorized?
Yeah, okay, so what it means is that, let's go back to that definition up here. So the problem is, so when it's not vectorized, a non-vectorized function is just a normal Python function, which means that it will treat the argument that comes in here just as a norm. There's no magic, right? So essentially what's going on in this code is you're calling my function, and the argument A is a vector. It's a Numpy array, right? So then you go into that function, and in that first line, you're now checking if that Numpy array is larger than 0. Right? So you essentially, on the left side, you have an array in this comparison, right? X is an array, and you're trying to check if that array is larger than 0, right? So that doesn't make any sense. Right? And so that's a non-vectorized function. If it was vectorized, and you call that function, you would Python would implicitly call that function for each element in that array, right? So you would actually call that function, in this case, 11 times. If you're calling the vectorized version of that, you're calling my function 11 times. For each element in our linspace array here, exactly 1 time. Does that make sense?
Yeah.
And so then what my function gets in as an argument is 1 number instead, namely the value of that element that you're currently looping over.
So the problem is where you compare the input to integer instead of an array?
Yeah.
Okay.
So anything that you want to, yeah, exactly. So yeah, exactly, for things like this here.
Yeah.
So we can test it, right? So this doesn't work, but if I now run the vectorized version of that, and I added this print x statement in here, so now my function is actually prints out x. And so I can say x equals. Okay, so let's see how often this x equals is called on my vectorized version. And you can see now that it's called for each element in my array.
The point of this is going back to the for loop of the elements compared to the array operation.
Yeah, exactly. So why are we doing this? And we're doing it because it's so much, well, for A, we can avoid writing a loop, right? So it's much, much nicer to, it's much nicer to be able to write something like this, where you can just vfunc A, and then you get another array out, right? So this, you could say B equals. And the second advantage is that it's much faster, because the loop over each array actually happens in C rather than on the Python level. Any other questions? Okay, so next week will be number, and profiling. Yeah, I think that's probably going to be it. And then afterwards, we will have 3 guest lectures. So I'll be on permission, probably. So the expected value is next Friday. So we'll see if I actually show up next Friday, not. But yeah, so at some point I'll just be gone for a few weeks, and then we'll have 3 guest lectures instead.